Hi, Assalamualaikum warahmatullahi wabarakatuh, my dear students. Today we are going to continue chapter 6, Aromatic Compound, by learning lesson 68, Chemical Reactions of Arene. We should be able to explain the chemical properties of benzene and its derivatives of electrophilic substitution reaction mechanism with reference to halogenation, nitration, Friedel-Craft Alkylation, and acylation. We need to be able to explain the influence of autopara or meta-directing substituent towards this reaction. And then we're going to learn the reaction of a benzene derivative, which is an alkyl benzene, by doing oxidation and also free radical substitution and electrophilic substitution of Alkylbenzene. As you can see here, the cinnamon stick has a benzene ring inside its cinnamaldehyde, and raspberry has phenol inside it. So what are the chemical properties of benzene? Benzene ring can undergo substitution reaction on itself, and if it has an alkyl group as a side chain, it can undergo oxidation and halogenation. There are two types of halogenation, whether it is a free radical substitution or electrophilic substitution, another substitution. Benzene can undergo electrophilic substitution. There are four types of reaction. Let's go one by one. The first one is halogenation using the reagent X2. X is a halogen Cl or Br. Using catalyst FeX3, you're going to get the benzene ring where X is substituted into the benzene ring. This is called halogenation. If we use bromine, it's going to be called bromination. If it use chlorine, it's going to be called chlorination. Simple, isn't it? The second reaction is when benzene ring reacts with HONO2 is the nitric acid. It's a concentrated acid together with a concentrated sulfuric acid with heat. You're going to form nitrobenzene, and this reaction is called nitration. The third reaction is called Friedel-Craft Acylation, whereby we're going to substitute R into the benzene ring. The R can vary, so depending on what you're going to put inside or into the benzene ring, just create your halogen here. Haloalkane. Halogen with R, and then the catalyst would be AlX3. The last reaction, the fourth one, is called Friedel-Craft Acylation, where you're going to use either acyl compound or acid anhydride compound together with catalyst AlCl3 and heat to form a ketone. This is a ketone where you have a carbonyl compound in the middle, a carbonyl group in the middle, and it is attached to a benzene ring and an R. So this is basically one of the formation of ketone. You can copy this down in page 237, where we are going to have there the mind map for all the reactions in chapter 6. You can already write down the synthesis of benzene and also the chemical reaction for benzene, which are these four reactions of electrophilic substitution. Okay, the next step is for us to learn the mechanism of electrophilic substitution. So in order to understand deeply regarding this mechanism, we need to use Kekulé structures because they are more appropriate for our mechanism. There are three steps: generation of electrophile, formation of Aranium ion, loss of proton to reform the aromatic ring. Let's consider this reaction where we have a benzene ring. We are drawing an expanded bond here with H so that we can see the process. The reaction between benzene ring with EY, where Y, for example, is a hydrogen atom. E can be a chlorine, a bromine, a nitro compound. It's an electrophile. It needs electron. This reaction is using catalyst to form a benzene ring where electrophile is attached to it. So what is step 1? The formation of electrophile. EY means that electrophilic site is the one that is electropositive, and Y is the electronegative. It is going to be bonded with catalyst, Y catalyst, like this, and it will be left with E plus, an electrophile, free to be attached to benzene ring. Step 2 is the formation of Aranium ion. As you can see here, this double bond has 4 electrons, and the pi electrons is going to be used to bond with the electrophile that is coming in. So it is going to form this single bond attached to electrophile, leaving with only a single bond here. Now we are going to have a resonance structure for this form of Aranium ion, because since this carbon is positive, the pi bonds, pi electrons here is going to move to the electropositive part of the carbon. So now we're going to have this double bond here, and this carbon would have the positive charge. Now, what happened is we're going to have another resonance whereby the pi electrons from the upper part here wants to be down here so that the double bond is formed at the positively charged carbon, leaving the top carbon here becomes a positive charge. These three resonance structure is all called Aranium ion. We call these three structures as the resonance stabilized carbocation ion because the electrons inside the ring keeps moving around, so that for the positive charge is distributed among the carbon inside the ring. This carbocation ion will be formed temporarily, and let's look at what happened in step 3. Removal of proton. to reform the aromatic ring. What happened here is the bond between this carbon and hydrogen is going to be used here to form back the double bond, making the positive charge here at this carbon disappear. So what happened is only electrophile now is attached to the benzene ring, and we got the product now. This is example 6.3 in your page 228, whereby we are going to do bromination on a benzene ring. This process would be needing Lewis acid, such as FeCl3, FeBr3, AlCl3. We can also use Fe and Al, the metal itself. So bromine atom acting as an electrophile is going to be attached to the benzene ring, forming a bromobenzene. Let's look at the mechanism in example 6.2. There you go. This is the bromine molecule, Br2. One bromine atom is going to be attached to the Lewis acid, FeBr3, forming a catalyst Y complex. So it will be left with a Br+. Br+ is the electrophile. Now, the second step, as you can see, the pi electrons is going to be used to attach with the electrophile. The nucleophilic site of the double bond is going to be donating its electron to this electrophile Br+, and it's going to form a positive charge at this particular carbon. What happened is, then in step 3, we're going to remove the proton here by using both of the electron in the single covalent bond to form back the double bond so that we can eliminate the positive charge in this particular carbon. Hydrogen then is going to be attached to the Br- that is forming a complex with the catalyst. So now we're going to get 3 different products. The major, of course, the one that we want is a bromobenzene, the byproduct HBr, and the catalyst free to be used for another reaction. This is one example of electrophilic substitution mechanism for bromination. You should be able to do all these steps on all 4 electrophilic substitution, which is halogenation, nitration, Friedel-Craft Alkylation, and Friedel-Craft Acylation. The second reaction of electrophilic addition of benzene is nitration. We're going to use nitric acid, which is concentrated, together with sulfuric acid, which is also concentrated, and heat. We're going to get nitrobenzene with water as the byproduct. Friedel-Craft Alkylation is the third reaction where Alkylbenzene is prepared. We are going to use Lewis acid as catalyst, and you can add in or substitute in any type of R you want. For this example 6.4 is inserting a methyl, but you can also use ethyl, third butyl, and so on, as long as it is supplied and attached to a halogen, which makes it a haloalkane. So this reaction we're going to learn again in the next chapter, haloalkane, but we're going to look at the product here, methyl benzene or toluene, which also is going to be undergoing several reactions after this, 3 of them. The fourth reaction of electrophilic substitution on benzene is Friedel-Craft Acylation. We can use either an acyl chloride or an acid anhydride. This too is the derivatives of carboxylic acid, which you're going to learn in chapter 10. So what happens here is the benzene ring is going to be attached to this part where you have the carbonyl group and an R. So we are going to produce a ketone by using the catalyst aluminum trichloride with heat. We also are going to use the same catalyst for the reaction of benzene with this acid anhydride, where we're going to take this part also, the carbonyl group and an R attached to the benzene ring. So this is basically the same product which you're going to have, and if you notice, this is a ketone. So we're going to learn also this reaction again in chapter 9, carbonyl compound. For benzene that already has substituent, the substituent will become a great effect on the reactivity and on the orientation. When benzene that already have certain substituent undergo electrophilic substitution, groups that is already attached to the ring will affect both the rate of reaction and site of attack. So we're going to look this at table 6.2. This substituent group can be divided into 2 classes according to their influence on the reactivity of the ring. An activating group is the electron donating group that causes the ring to become more reactive than benzene. An example of an activating group, or we call it electron donating group EDG, is listed in table 6.3. An example is an amino group, a hydroxy group, an R, and so on. For example, here we choose a methyl group. This is a toluene. What happened here is toluene will release electron to the ring, making the Aranium ion more stabilized. This effect will make it form a faster product, and it has a higher rate of reaction as nitro group is going to be attached at the ortho position. Another group is deactivating group, which we also called electron withdrawing group, or EWG. This group will cause the ring to be less reactive. For example, a carboxyl group, a cyanide group, and nitro group. Here is an example where we choose a halogen chlorine, it is a EWG. It will withdraw electron from the ring, making the Aranium ion destabilize. So it is going to form a slower product where it has a lower rate of reaction. Nitro compound is going to be attached at ortho position, as we see in table 6.3. This is the effect of having chlorine inside the ring. As you can see here, in example 6.6, we should be able to arrange any benzene ring with substituent according to their reactivity. So we know that hydroxy group is an EDG where it is going to activate the ring, so it has the highest reactivity, followed by a benzene ring on its own, followed by an EWG, but it is auto-para-director. Auto-para-director is more dominant than meta-director, which is the nitro group. So nitrobenzene would have the least reactivity among these four compounds. This is a bit of explanation. Nitro group is the activating group, which is a meta-director. It will withdraw electron from the ring and destabilize the Aranium ion. This is your answer scheme, basically how to explain the reactivity of benzene with substituent. Chlorine is a deactivating group, but it has an auto-para-director. It will withdraw electron from the ring and stabilize the Aranium ion. It is stronger than nitro group because it is an auto-para-director. Hydroxy group is an activating group. It will release electron to the ring and stabilize the Aranium ion, making it more reactive. Question number 2. Let's compare between substituent CF3 and CH3. Of course, methylbenzene or toluene would have the most reactivity because it is an electron donating group, and having halogen inside the substituent, making this compound is the least reactive among the three. How do we explain this? So CF3 is a deactivating group, a meta-director. It will withdraw electron from the ring and destabilize the Aranium ion, making it less reactive compared to when we have a methyl group attached to the benzene ring. Methyl group is an activating group, which is an auto-para-director. It will release electron to the ring and stabilize the Aranium ion. So these are your answer scheme for explaining why certain benzene ring attached to a substituent, whether it is more reactive or less reactive. Now, another important thing that we need to look at is the effect on orientation. Auto-para-directors will direct the incoming group into auto-para position 1, 2, and 1, 4, whereas meta-directors will direct the incoming group into meta position 1, 3. There are 3 classifications of directors. We have activating auto-para directors, and we have deactivating auto-para directors. The third one is deactivating meta-directors. These 3 categories can be seen easily in table 6.3. This is an important table for you. As you can see here, The auto-para-directing activators are methyl, NHCOR, OR, the ether, OH, the hydroxy group, NH2, amino, and also NHR, NR2, the activating increasing by the arrow shown to you. R is the most, is less reactive out of all. Why? Because all the other groups here, they have lone pairs. As you can see, shown to you here, they have non-bonded electron pair. So these electrons, when they are released into the benzene ring becomes more reactive. Auto-para-directing D activators are the halogen groups or halogen atoms. It is fluorine, chlorine, bromine, and iodine. Here is the list of metadirecting D activators. You have an aldehyde on top, COR, COOR, COH, the carboxylic acid, cyanide or cyano, SO3H, NO3, nitro, NR3. So the increasing the activation is going downwards, and the general structure can be seen here. It will be connected to Y, whether Y can be electropositive or electronegative. It would have a full or partial positive charge on the atom bonded to the benzene ring. We have another one here, CX3. Let's do example 6.7. As you can see here, the first question is on toluene. Toluene already has an alkyl group attached to it, making benzene ring more reactive than before. And methyl is going to become auto-para-director. It is going to tell NO2, which is going to enter the molecule, where it is going to be. So methyl is an auto-para-director. We are going to do nitration here. So we're going to produce two products. Okay. I like to do a portrait benzene. It's not very nice. This is CH3, and we're going to put NO2 over here. This is one product, and then we're going to do another product as CH3, and NO2 would be over here. So this is the major product for the nitration of toluene. Next, NO2 is attached to the benzene ring. This is a nitrobenzene. Where is NO2 in table 6.3? It is a deactivating metadirector. So we're going to have CH3 is the R that we're going to insert into benzene ring, because this is Friedel-Craft Alkylation. So we're going to have only one product. This is the benzene ring. Attached to it is NO2. Alkyl is going to be attached to carbon number 3. So CH3 is over here. So that is how you substitute an incoming group as for the benzene ring that already has a substituent. Example number 3 here is a Friedel-Craft Acylation. We're going to cut the bond here And then we are going to draw a benzene ring. This is supposed to be like this. Okay, so Cl. This is an autopara director deactivating, right? So Cl is going to be here, for example, and it's the incoming group C double bond O CH3 is going to be attached to carbon number 2 since this is an auto position, and it is also going to produce another compound Cl, whereby the incoming group is going to be situated at para position. So both of this is major product. Number 4, this is an alkyl group as well. It's an ethyl, and it's going to undergo bromination. So we're going to have autopara position as well. This is the ethyl, tuan rumah, is going to put bromine on the carbon number 2, and also another product, another major, would have bromine at carbon number 4. So this is autopara director. Both of this is a major product of the bromination of ethyl benzene. Okay, this is Friedel-Craft Acylation using acid anhydride. So we're going to cut the bond here. We have a chlorine. Chlorine is an autopara director, so we're going to have two products whereby chlorine will direct the incoming group to be situated at carbon number 2, and another product is going to be situated at carbon number 4. So these are the autopara position of the incoming group C double bond O CH3 when Cl is the one that is already inside the benzene ring. Chlorobenzene is the reactant here. Okay, the last part of chemical reaction of benzene is we want to look at the reaction of Alkylbenzene. So when we have an Alkylbenzene, where we can have methyl, we can have ethyl, we can have isopropyl, it is going to be undergoing halogenation and also oxidation. There are two types of halogenation. Number 1 is free radical substitution. We're going to use X2 in UV light. So the X is going to attack or is going to react with the carbon outside the ring, meaning the alkyl part. But if we have X2 with Lewis acid, we are going to have a product whereby it's going to attack the carbon inside the ring. So it's going to undergo electrophilic substitution, not free radical substitution. The difference between these two would be only the condition, which is UV light for free radical substitution and Lewis acid for electrophilic substitution. Right. And then the third one cannot be mistaken because it's easy. When Alkylbenzene is being oxidized by potassium permanganate and sodium dichromate with H+, acidic environment and heat, it's going to form benzoic acid. So however, how many carbon that you have in R, even if it's isopropyl, even if it is pentyl, it is going to become benzoic acid. All the carbon would be gone because it's being oxidized, and what is left is COH, which is benzoic acid. So they're going to form carbon dioxide and H2O. Let's look at the first one. Halogenation, free radical substitution of alkylbenzene. As you can see just now, are attached to benzene ring. When reacted with X2 under UV light, it is going to produce a benzene ring attached to Rx. Example 6.1. This is an ethyl benzene. So let's draw the product. Okay, I'm drawing the benzene ring first, and then I'm drawing the CH2 and CH. This is the reactant. Okay, I am expanding it. So which carbon is going to be attached to Br? We have to look at the classification of carbon. This is the this is the primary carbon, and this is the secondary carbon. So which one would be more stable when we do free radical substitution? It would be the secondary carbon. So we are going to remove one H, and then we're going to put Br over here. So this is the product of free radical substitution of an ethyl benzene. The second halogenation is electrophilic substitution of alkyl benzene. We're going to produce two products since alkyl is an auto-para-director. So what we're going to have is X is going to be substituted into carbon number 2 and also carbon number 4, auto-para. Example 6.9, question number 1, ethyl benzene also. So we are going to draw a benzene ring with an ethyl attached to it. Ethyl is going to direct Br to be substitute at carbon number 2, and another one, it is going to be substituted at carbon number 4. So both of this is the major product of electrophilic substitution of ethyl benzene. The last reaction for chapter 6 is oxidation of alkylbenzene. We are going to have alkylbenzene reacted with potassium permanganate or sodium dichromate under the acidic condition and heat. They are going to produce benzoic acid. These two reagents are called strong oxidation agents. Oxidation will take place at the benzylic carbon. Which one is the benzylic carbon? The benzylic carbon is the carbon that is attached directly to the benzene ring. If this carbon has one hydrogen at least, it can be oxidized. But if the benzylic carbon does not have any hydrogen attached to it, oxidation process cannot occur. So benzoic acid will not be formed. Oxidation test is one of a chemical tests to detect the presence of alkylbenzene. So the observation is, if we use potassium permanganate, purple color will turn to colorless and brown precipitate will form because MnO2 is going to be produced at the bottom of the test tube. And then for the second one, when we use sodium dichromate, orange color will turn to green. Let's do example 6.10. given to us is methylbenzene. So what we're going to have is a benzoic acid. That's it. Of course, you can also add the byproducts, but this is not compulsory. Now we have, what is this? CH3, there is 2 CH3. And look at this benzylic carbon. Does it have a H? Yes. So if it has a H, we can produce COOH. We can produce benzoic acid. So this is also the product. See, I told you it's easy. It's just a matter of us detecting whether the benzylic acid has hydrogen or not. Now, for this one, does it have a hydrogen? No, right? So there would be no reaction here. Benzoic acid will not be formed because the carbon that is attached directly to the benzene ring does not have any hydrogen atom. It cannot be oxidized. This is your homework, practice 6.3. We want you to draw the structure of A when this product is being substituted using free radical substitution, and then this is the second halogenation when it undergoes electrophilic substitution, and this is when that product becomes benzoic acid. C would be benzoic acid. That's your answer. Number 2, predict the major product form when aniline is nitrated. Okay, write the whole equation. Nitrobenzene is brominated. So where would the incoming or the products will be? Number 3, cyclohexene and benzene can react with bromine in different conditions. So it is UV light and Lewis acid. So you have to show both equation there. And you have to differentiate the condition. Now give the type of reaction. What are the 2 types? I've mentioned it to you a few times now already. And write the reaction mechanism for the reaction of benzene with bromine. Which one? I think maybe the ones with Lewis acid. Or if it's free radical substitution, you can also do it. Why not? We have already learned it in chapter 5. Right. That's all for now. Thank you very much for listening, and I hope you will be able to digest chapter 6 well. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Bye.